Welcome on another wireless mobile communication lecture series. Uh, Previous lecture we have seen the mobile radio propagation. Now we have moved uh, to forward. Before we are moving to forward, we resume the recap once again. We already know that the scale large scale path loss model. In this topic, this propagation model gives the estimate the mean signal strength of the transmitted signal in order to identify the cover area when the transmitter receiver distance is very large. So it is called the large scale path loss model. Here to understand how much the loss that will be occur within the larger transmitter receiver distance. Now let us we will understand first why we required a path loss. When we transmit the signal in a free space, there are various obstruction and then the various parameter which leads the attenuation. Due to attenuation we have achieved the path loss. The largest the path loss of the signal means we require to calculate the path loss. So path loss of the signals here to model, and after that we have move on smaller path loss model. The smaller path loss model, there are the flexibility to calculate the attenuation in the signal. Now let us see the small scale path loss model. The propagation model, the propagation model that characterized the rapid fluctuation of the receiver received signal strength over a very short travel distance, or we can in another word, it's take the short time duration, that is known as the short time duration, or known as small scale fading model. The propagation model that are characterized by the rapid fluctuation in a signal in the shorter time duration between the transmitter or receiver are called the smaller scale path loss model. After that we have moved our the main topic, that is known as free space propagation model. Free space propagation model. In this topic, the free space model is used to predict received signal strengths when the transmitter receiver have a clear unobstructed line of sight path between the transmitter and receiver. And when the signals are propagated to start from its originate transmitter antenna towards the receiver antenna, there is no obstruct, so your waves cannot be delayed here, attenuate, or you can say divert here, reflect, or it takes diffraction or any other scattering phenomena, so it can be reached within the same predictable time, and it is follow the line of sight between the transmitter or receiver. If this thing is happened, then we can say the free space propagation are taking place. So we can write the free space propagation model is used to predict received signal strengths when the transmitter and receiver have a clear unobstructed line of sight path between the transmitter and receiver. So in a free space model, it is assumed that the free space mean that is line of sight between transmitter and receivers are taking place. If there are no obstruct, then we can able to calculate a signal strength of the received signal, and this thing is calculated by the Friis space equation, that is known as Friis equation, which is given by transmitted power at distance d is equal to received power at distance d is equal to transmitted power, gain of transmitted antenna, gain of received antenna, wavelength square of the wavelength between them divided by 2 pi square d square of area and aperture or dimension of the antenna. The free space, this equation is say 1. This is the free space power received power received by a receiver antenna which is separated from radiating transmitter antenna by a distance t is given by the Friis equation, which is the equation number 1, where PR at distance, power of received distance at R receiver, it is the received power. It is the known as received power. P of T is known as transmitted power. G of R is known as receiver antenna gain, and G of T symbol is referred to transmitter antenna gain, and small d is the transmitter receiver separation distance, and L is referred to factor loss, or we can say path loss. One another name is system loss. These are the terms is used in equation 1. So the free space that is been received by the receiving antenna having the certain distance d between the transmitter and receiver antenna, this received power is given by this Friis equation, and here the gain of antenna GR and GT is given by the antenna aperture divided by the surface area. Here AE, capital A, stands for antenna aperture. And it is also known as effective aperture, where lambda is equal to wavelength, and we know that wavelength is C by F, where F is can be written as C multiplied by 2 pi by FC WC, where WC is a angular frequency. Angular frequency. One thing is kept in mind. We are using the antenna. This antenna is isotropic radiator and is an ideal antenna when radiates the power with unit gain. It is uniformly in all direction and it is often to use as a we can say reference antenna gains in the wireless communication, wireless radio mobile communication system. The effective isotropic radiated power, that is written as EIRP. EIRP is stand for the effective isotropic radiated power. ठीक है, so it is right. EIRP is the product of the transmitted power and gain of the transmitted antenna. So here this is equation number, this is one is 2, this one is 3. All three equations which are using here, now we are going to give a proof, derivation proof. So started from the path loss, to derive the path loss. So let us see what is meaning of path loss. The path loss meaning, this is the derivation section. So in this the define the path loss which presents signal obstruction, or you can say attenuation, is defined as the difference in decibel, right, decibel in dB between the effective transmitted power and the received power. The path loss for the free space model when antenna gains are included, and it is written as or given by PLDB. It is noted, it is written as PLDB, path loss. So path loss is tan log transmitted power to the received power, and it can be written as minus tan log, if we put the values transmitted gain and received gain and divided by its area, And in this equation, in this uh, uh, terms, when the antenna gains are excluded and antennas are assumed to having a unity gain, then this given equation is reduced, and then we have the another path loss. Here what we do now, we do when antenna gains are excluded, then the equations, then the terms antenna are assumed to have unity gain, and path loss is given by, after the reduction, putting the formula, assuming that gt and gr is equal to 1, so it reduce and come into this form, power to the transmitted power to the received power minus 10 log, and this GTR transmitted gain and received gains become 1, then formula is like this. So we having the another terms where the taking the unity gain of the antenna. Let us, we can see one more, there is concept for far field, and that is the Fraunhofer region. The Fraunhofer region of a transmitting antenna is defined as the region beyond the far field distance df, and at which it related to the largest linear dimension of the transmitted antenna aperture and wavelength. Now this df